the group mainly deals and discusses about CO2 storage site selection, of course, subsurface monitoring, and all different aspects of CCS, really. And I am one of the committee members. We have about 20 committee members across different countries and different regions. Yeah, we have a map here. You can see how we're distributed, coming from both operators, service companies, as well as academia. So it's quite a varied group of people. And if you are interested in joining us, of course, we shall have QR code on one of the slides. So please do join us and get in touch. You'll be like to be part of the committee as well. Of course, we organize activities like this webinar. This is already the second webinar that we have organized, as well as participating to the EAGE conferences, and particularly the annual, as well as the GET conference, hosting dedicated sessions and workshops, as well as organizing networking events and educational as well with students. So yes, please feel free to get in touch, and also you can use the QR code on this slide if you would like to join us on LinkedIn and become one of our members. So this was the quick introduction. Now I think you all want to listen to what KP has to say. So I'm going to start with a quick introduction. The title of the presentation is Distributed Acoustic Sensing for Monitoring and Imaging. And KP has a background in geology and in geophysics from the University of Texas in Austin. He's covered different roles in his career, starting as a petrophysicist, as well as a well planning geologist, and then later processing geophysicist, and is still currently based at Viridien, formerly CGG. In particular, over the past 5 years, KP has specialized in imaging and monitoring using distributed acoustic sensing, or DAS. So today he's going to give us an overview as well as an introduction on DAS and an overview of different applications across the oil and gas and CCS projects. So I think KP should be ready to share his slides now. So I'll pass the microphone to him. And yes, we are going to have some time at the end for questions. Thank you.
Yes. Yeah, I will share from my side. Thank you for the introduction, Francesca. Let me just share the right PowerPoint. All right. Okay. So everybody can see the presentation?
Yes, we can see it.
Okay, good. Good afternoon, good evening, and good morning, everybody. So today I will be talking about DAS for subsurface imaging and monitoring. As you can see, the title here was slightly different from what Francesca just showed. I changed the title to Active DAS, so because I want to highlight the majority of the slides I have today is active DAS. I do have a little bit of materials from passive DAS, but most of them are active DAS examples. Okay, it works. So I have 4 parts in this presentation. I will start from DAS 101. It's going to be very quick. I think most people on this call, probably everybody, knows the principle of DAS, so that's a very short one. Then I will move on to the challenges and for active DAS data processing, and I will also mention a couple of the solutions that we have developed in the last couple of years to tackle those challenges. Then I will move on to the field examples. Actually, I have quite many examples today covering DAS VSP and also the surface DAS. I also have a little section called Beyond Imaging, so that's not just the subsurface imaging, for example, velocity model build or FWI using the DAS. And in the end, I'll wrap up with a summary, and hopefully we still have enough time to have some discussion, and I can answer questions as well. So I'll begin with the DAS basics. So what is DAS? The very first question I heard somebody said DAS stands for dig and see. And of course, this is a joke, and a very good joke actually. DAS stands for distributed acoustic sensing. The picture on the left is a photo taken by my colleague Alba. If you look very carefully, you can see there's a fiber optical cable will be buried in this trench. So how DAS works? And the fundamental thing about the DAS is the backscattering in the optical fibers, or rarely backscattering in the fiber. This is an analog showing, you can see as from one side, when we inject a laser pulse into the glass, and the light will travel in the total internal reflection and go through the fiber, and you can see the come out from the other side of the fiber. So bear with me. Do I have a point options? I do here. But again, if you look very carefully, you can see there's a little bit of light coming up from the side on the left as well. So that's because of the scattering. So what is backscattering is the light path or optical traveling path, as you can see here. Actually, if there's no scattering, we shouldn't see this optical light path at all. And just because of the backscattering, now we can see how the light travels inside. So that's the fundamental that we can utilize this for DAS. And this diagram shows that once you have the fiber, well, by the way, I forgot to mention that in the previous slide. Well, the reason we have this backscattering is we have the natural impurities in the glass, and that's always the case. So here in this diagram, you can see I highlight this little impurities in the red dots, and this is the blue one. It's a section along the fiber, and when the fiber is in a quiet environment or in a, let's say, a background environment, the fiber will stay the same as it is, like just being manufactured. However, when you have an acoustic wave or seismic wave hitting the fiber, it will cause a very, very small elastic deformation at that location, and this little deformation, I'm talking about a very, very tiny deformation, but this tiny deformation will create a different optical path, and that will lead to different phase of the returning light or backscattered light. And the bottom, as you can see, the blue one is the light coming back from the fiber without any interference. And the orange one is when you have some energy hitting your fiber and generate some deformation, then you're going to create some, in this case, the diagram shows delay, but could be earlier as well. There will be a phase difference that you can utilize, and you can extract from here. And once you have this phase difference, that you can estimate a seismic signal. So that's how DAS works. Very, very, very simple. About the geophysical applications of DAS, well, beyond the geophysical, there are a lot of applications of DAS. I'm not going to talk about that today, but I think many people are familiar with that. They can use DAS for, let's say, monitoring the infrastructures and even study or tracking animals, let's say. But today I'm going to be talking about the geophysical application, basically seismic. So the application starts from, I would say, early 2010s, and started from the vertical seismic. I think that makes sense because that's the case. You normally have a fiber in a well that you can use for monitoring the injection or production of the well, the temperature and flow rate and in the borehole. And then people realized that we can use this fiber to record the seismic as well, because this essentially will be a pseudo VZ measurement, which is not not exactly VZ, but the pseudo VZ, which is not hugely different from the conventional geophone VSP. So there are a lot of very good results have been achieved since then. One of the quite famous example is the Quest CCS project in Canada. So encouraged by the many successful examples of DAS VSP, there very recently, I would say, in the last maybe from 5 to 6 years ago, people started testing using surface cables to record seismic. There have been quite a few examples from industry. Those examples are from, a majority of them are from using seafloor cables. This is one example here, as you can see in the middle. Those cables, that can be any cables, as long as you have optical fiber in that cable, you have the opportunity to use that as a DAS cable. Another application is, of course, on the land. A lot of hydrocarbon projects or CCS projects are on land. So, however, to my knowledge, that I haven't seen that many very successful DAS application from land yet, because it will face the same issue that the conventional land seismic will face. That's the very low signal to noise ratio. But there are indeed a lot of studies, a lot of research from land DAS, mostly from I would say mostly from academia. But again, the majority of the successful ones from the industry are utilizing the offshore cables. This is one example of one of the offshore cable, and in this case, this is actually a power cable and a subsea high voltage DC cable. As you can see, it's very big cable, very thick. And here highlighted by this red circle, you can see this cable comes together with some fibers for telecom purpose. And on the right-hand side, you can see this very tiny fibers. There are actually, if I remember correctly, there are 12 fibers for this specific cable. And you can use one of this fiber to record DAS if you plug it in the interrogator box. Okay, so this is a very brief recap of the principle of DAS. And now I will be moving on to the data processing. I will divide this part to two different categories. The first, I will start from DAS VSP, then I will talk about surface DAS later. So for DAS VSP, here you can see two shot gathers. Actually, there are same shot gather, but being at same location, but being acquired at a different time. On the left is the shot gather that being acquired when the well was quiet, the production of the water injection was switched off, and you can see the very nice signals here. It's all of these downgoing events and upgoing events. There are some noise, as you can see as well, but not that many. It's quite a clean, quite nice DAS data. But on the right-hand side, once you acquire DAS from active well, in this case, the water injection was switched back, you can see this significantly increased noise level. So for DAS VSP processing, the biggest challenge is to attenuate this production noise or injection noise. So there are a lot of method to denoise VSP, and I'm not, well, there are very traditional or conventional ones like deep filtering or some rank reduction to attenuate the more random noise or impulsive noise attenuation. I'm not going to talk about this today due to the limit of the time, so I will just present two quite advanced method. Two method that we developed recently. So one method, the first method is called model-based noise attenuation. Again, on the left, you can see some very noisy data. The very first panel is common receiver gather, and the second panel is common shot gather. And the two panels on the right-hand side after denoise. And the denoise method we used here is we derive a signal model. Or we recycle the signal model that we generated during the deep blending process. So it's a sparse signal model in the TOPI domain, and we then use this model as a guide, as a signal model to separate the noise in the input data. So to achieve the separation of the noise and the signal, and on the right-hand side, you can see the output is quite nice. And if we compare to the input again, there are some signals here. I highlighted these red arrows, but very, very heavily masked or contaminated by the noise. And the first break here as well. But now after this denoise, you can see it's very effective. The underlying noise now become much more visible. And the second method is the machine learning method. So it's basically quite a, I would say it's quite a popular research area at the moment, especially for those VSP denoise. So you first train a deep neural network model, then use this model to predict the clean output. I'm not going to the details of this one. There are a lot of different ways to train a model. You can rely on, maybe you have a small subset of clean data that you acquired, or you run some heavy processing on a small set of the data that you generate some target, and you can use that for training. Or you can also do some training that without any training data set. So there are different ways of doing this. I'm gonna skip that, but this is another way you can attenuate the injection noise effectively. So that's for dust VSP. Then the next thing is the surface dust. So what is the major challenge for surface dust processing? Here you can see a shot gather here. This is an example from marine cable. And I highlighted some man energy areas, and on this shot gather, you can see very, very nice diving waves here, and very nice surface waves as well, very, very pretty. So those are very, very good energy that you can use to derive, let's say, near surface velocity profile. But regarding P wave imaging, so we are looking at this part, this area. So in this area, you do see some reflections, but if you look very carefully, those majority of these reflections are very strong PS wave or the converted reflections. There are some PP reflections here. If you can follow my pointer, there are some of the PP here towards the far offset, some of here as well, and here, but they're much weaker compared to the converted PS waves. And the main reason for this is because for surface cable, the dust cable become essentially a horizontal sensor, so it will be much more sensitive to the shear wave than the P wave. So the biggest challenge for surface dust processing is for surface dust PP imaging is to attenuate this PS, because if we do the PP imaging, then the PS will be noise. So we need to remove the strong PS and recover the underlying very weak PP. That's the biggest challenge for surface dust processing. And also, I'm going to just mention two methods here. The first method is more a traditional method, so that is based on the different velocity of the P wave and S wave. So by applying some velocity correction, let's say, for example, NMO, that you can flatten your P wave, but you're going to have some residual move out on your PS wave. So and utilize that, you can apply some filtering or some radon method to attenuate the residual move out, which is the PS, to achieve the PS wave attenuation or to achieve the PP-PS suppression. And in this case, you can see on the right-hand side, that's the result. And I highlighted the PS events on the left, but they are largely being removed. Not 100%, you can see some residuals here, but I would say it's still quite effective. The majority of the PS is being attenuated, and we end up with having this PP gather. And the second method is I call it the legacy assisted method. This is useful because the first method traditionally, this is the traditional method that it works for some works very well for some data, but sometimes it's less effective if your velocity of your or if your move out or discrimination between your PP signal and PS signal is not that big, for example, very shallow water, or your ice velocity is not that slow compared to 2P, then this velocity discrimination method will be less effective. It still works, but less effective. Then you can try another method, that is to utilize an existing data set, in this case, existing reflectivity. So you can demigrate that existing reflectivity to generate a signal model that will be, well, by the way, that reflectivity is a PP reflectivity, and you demigrate that using Py velocity. So you can get a PP model, which is the second panel here. And I use that to separate or to estimate the noise and the signal ratio in the input data. And then you can do some, let's say, the signal to noise ratio thresholding, and to achieve the PP and the PS separation. And that's the result on the right-hand side. The very right is the PS, and the second to the right-hand side is the output PP. Now you started to see the very weak, very weak PP signal that is very hard to identify in the input data. So this is a very effective method, but it does require you have some legacy reflectivity that you can use to generate the model. Okay, so these are the two, in my opinion, these are the two major challenges for the dust data processing. Like as I said earlier, just a very quick recap. For dust VSP, the biggest problem is the injection noise attenuation. For surface dust, the biggest challenge is to separate PP from the very strong PS. There are also other challenges. One dealing with dust data. Where, in my opinion, again, these are regarding the imaging. Those challenges are the secondary challenges. That they're quite well known, quite that's very important as well. But yeah, I think there are secondary challenges. I will just very quickly mention them. And so the first thing is the angle sensitivity of dust. Everybody is quite aware of this. And here shows a profile of a VSP application. So the green one is the fiber or the borehole. So, and the red here, from white to red, indicate the sensitivity of the seismic waves that hitting this vertical fiber. So as you can see, as we mentioned earlier, that for the vertical dust, then the sensor itself, the fiber itself is essentially a VZ recorder. So when we look at the near angles from 0 degree to let's say 45 degrees, the signals are still very good. Amplitude are quite strong. It's only in this part, very high angle, that mostly will, from the contribution of very far offset shots, are very weak. But this part is not the area that we use for imaging anyway. So the angle sensitivity issue for dust VSP is not it's not that bad problem, I have to say. However, if we look at it, surface deployment of the fiber on the left, you can see the similar diagram, but the fiber is horizontal, so this is the case for surface seismic. Now the angle sensitivity become an issue. You can see the angle here, that the angle we normally use, let's say 0 degree or 5 degree to 35 to 40, that angle range is the useful range that we normally use to generate subsurface imaging, and that range is being affected by the directivity or the sensitivity a lot. And here you can see two modeled receiver gather, and this is the time slice. The one in the middle here, this one, the red curve indicates the orientation of the cable, and you can see the dimming zone here and here. They're like from the y direction, so you can see the wave hitting the cable from roughly a normal direction. Then your recorded amplitude of dust is much weaker compared to the direction that along the cable. We refer that as x direction or axial direction. Compare this to the hydrophone, which is of course 360 degrees. You can see there are some data is missing, that we have less data compared to the hydrophone. And then in the bottom is, this is a seafloor cable. The red one indicates the orientation of the cable. It's not a straight cable. In this case, it's turning directions here. And each little circle here is the IMS extracted along the direct arrival. And you can very clearly see the blue area for each circle. The blue area indicates the very weak amplitude. That's the same area like this one. So you can see how the orientation of the dimming zone is consistent with the orientation of the fiber. So the way we handle this in the processing, how do we compensate this part of the amplitude? Because we know that this is also quite well known in the relationship that the P wave amplitude for DAS is scaled by cosine square. So we can simply divide this cosine square to achieve the amplitude recovering or amplitude compensation. But one issue with this method is this method doesn't distinguish noise and signal. So it will, when you apply this compensation, it will boost the noise as well. That's the case, especially for the very, very high angle here, like a very small angle, like the vertical angle, let's say within 5 degrees, because then in that case, the cosine square theta will be very, very small, and your signal is very weak there. So if you apply this division to compensate the amplitude, then you're going to really boost a lot of noise at a very near angle. So practically, we apply this compensation, but limited the angle range for this application. Some other challenges regarding DAS is on the left showing the dynamic range issue of DAS, because we all know that the DAS is a phase measurement. So whenever you have a phase measurement, you're going to face the 2 pi cycle skip issue. That's also the challenge for DAS as well. So when you have a very, very strong like energy hitting the fiber, let's say, if your source is too strong, or if your source is too close to the cable, you're going to generate some very high amplitude energy hitting the cable. That will exceed 2 pi. It will become whatever, like 4 pi, 6 pi, and it won't be able to recover. If it's a small overshooting, that you can do some phase unwrapping, but that's only limited to if that overshooting is less than 1 pi. But if it's more than a full cycle, there's no way you can recover that. So that's another big issue for DAS processing. This is particularly the case for surface cable. For DAS VSP, because the sensors or the cables is located in the formation. So when the energy reaches the fiber, is already weaker compared to the surface fiber, so you normally don't have this issue for DAS VSP. So it's only an issue for surface cables. And the way we mitigate this in processing is we apply some reconstruction. So because the main area being affected is the first breaks or direct arrivals, as you can see here. So we can use some external wavelet, let's say source signatures, that model 6 source signatures, or some near field hydrophone recording to generate some source wavelet. Then you can use that wavelet to reconstruct or to replace the broken or corrupted or over some saturated samples. That's the result we achieve here. But this works for if the saturation is not too bad. But if it's very bad, like the one on top, it's quite a challenge to fix this issue completely from the processing side. And this will generate, actually it will generate quite a lot of problems in the processing sequence. The last challenge I would mention today is the uncertainty about the DAS virtual channel or DAS virtual receiver coordinates. So this is something fundamentally different when compared to the conventional seismic. The conventional, no matter it's a land or offshore streamer or offshore ocean bottom node, you have very good control in the receiver locations. You have a GPS that you can use, but that's not the case for offshore cables. many times you don't know the exact location of these cables, and even you have a very good control of the cable location, you still don't know the XY coordinates for each DAS receiver, because the DAS is where the signal we have, where the signal being back scattered. How do we know that? We know that by looking at the how far the light has traveled inside the fiber, and that distance is not exactly the same as the how long the cable is in reality, especially when the cable is not straight. All of the fiber is not straight inside the cable. So for surface dust processing now, almost always the first step is to derive the coordinates for each dust receivers or each dust channels. And the typical method we used in our processing is we use some travel time inversion to locate each receiver, especially when you have a 2D or 3D short carpet above your cable, and then you have the great advantage to recover the accurate location of each DAS receivers. Okay, and now move on to the MAN section. I hope I didn't use that much time so far. Yeah. The MAN section for this talk is I'm going to demonstrate some field examples from both VSP and Surface DAS, and a few more examples in the end. So we'll quickly go through these examples. There are quite many examples here, but they are not duplicate to each other. They all here, I put them here for a reason. They're all different from each other. So for the DAS VSP, I will show you a couple of examples that we use different migration methods to image DAS VSP data. So the first example here is on the very left is the traditional RTM using outgoing primaries, and the second panel is the mirror migration, mirror ITM using the first order CBET multiple. So the both migration methods are using single reflections. So then we merge these two together, we can get this image at the third panel. As you can see, it's actually quite good compared to the ocean bottom cable or ocean bottom node. Both at the overburden and also at the reservoir. I think for this example, the reservoir is somewhere here, and it's quite nicely imaged from this data set. So the second one I want to show you is, as I said earlier, the first example is using the single reflections of both upgoing and downgoing. And this example demonstrates that for the upgoing, we still use the single reflection primary energy, but for the downgoing, it's not just the first order CBET multiple. In this case, we use the full multiple wave field. It's the entire downgoing wave field, all orders of multiples. So we can generate a very extensive, because we utilize the high order multiples, we can generate a very extensive coverage, especially at the shallow section. Actually, we can achieve a size of the image same as your short carpet. Again, those two migrations have been conducted separately, and if we put them together, we have this third panel, and we can compare this one to a PM result. By the way, the PM stands for Permanent Reservoir Monitoring System. It's a system consists of thousands of ocean bottom nodes, and those nodes are connected by cables. And later on, we'll show some data from the PM cable as well. But yeah. So it's a PM is a system ocean bottom node, if you haven't heard about this before. So then the third example here. Well, by the way, these two examples are both single well, single cable, and the third example I'm going to show you is a multiple cable example. As you can see, the acquisition setup here, or acquisition map. There are two islands here, and the red and the blue indicate the short carpets for the two islands. And there are like 8 wells being drilled from each island here. This is an artificial island. And on the right-hand side is a map of one of this island. It's the North Island. And one thing you would notice immediately is there are a lot of acquisition gaps here, and the biggest one is the one around the two islands. So this is actually quite a big gap. It's more than 1.5 kilometers. So the very first thing we need to do is to fill these gaps. What we did is a multi-pass regularization. So basically, we fill these gaps gradually from the edge of the existing traces. and eventually we fill the large gap and get the result on the right-hand side. It's yeah, as you can see, it's quite nice, but of course you can argue that this is not real data, it's being interpolated, and that's true. But the main advantage of doing this is for the benefit of the migration. So that's the image on the bottom. As you can see, if you don't fill these gaps, you're going to end up with having a lot of migration artifacts or residual migration smiles if you know the migration method. So if we migrate the data again after applying this multi-step regularization, you can see again this part is not very good, but then your migration artifacts is largely gone compared to the one before. So really this helps migration a lot to generate a cleaner migration output. So the final imaging method we used for this data set or for this project is we call it joint primary and multiple imaging, or JPMI. Recall that the previous two examples, or the last example I mentioned, that we used the full wave field of the downgoing plus the primary only upgoing. So that's like up and primary only plus all the multiples. But in this case, we used the entire wave field. So this includes all the upgoing events and all the downgoing multiples. So it's essentially a full wave field imaging. And as you can see, when compared to the OBC, we generate a very. Also, by the way, this migration is in one step. The previous examples that we do the upgoing migration and downgoing migration separately, then we merge the image together to form a single volume. But in this case, this JPMI algorithm, by the way, is our latest technology that we developed. So you do this in one go, then you can generate this single, like almost full field size volume. And quality-wise, it's also comparable to the OBC. You can see all of these man reflectors. Okay, so now I will be moving on to some 40 examples of using DAS-VSP. The first one here is back to single cable DAS application. This is offshore in North Sea. So there are two things worth to mentioning here. The very first thing is when we look at the panel on the left-hand side, that's the DAS-VSP image. And compared to the second panel, which is the image from the PM, we can already see, even on the imaging side, we already see some benefit of doing DAS-VSP, especially if you look at its top reservoir and best reservoir, they're better imaged in the DAS-VSP compared to the surface PIM. And this is likely due to the proximity of the fiber or of a cable to the reservoir. And another possible reason is that for this surface PM, that this location is under the production platform. We do have an acquisition gap for the PM node in this place. So that's maybe another reason that why DAS-VSP image this top reservoir is better than the PM. Okay, now if you look at the 4D on the right-hand side, this is the 4D from the PM system. You can see it's quite clean and a very obvious 4D signal here in between the two, the top and the best reservoir. And this panel here is the 4D from the DAS-VSP. Obviously, it's noisier and overburdened. There are some residual not being fully cancelled, but I think it's quite obvious that the 4D signal, same 4D signal is also visible here. What is even more amazing for this project is that you can see those signals, those 4D signals, you can see them because I boosted 15 dB of the amplitude. So that is to say the 4D signal is actually very, very subtle in this case. But using the DAS-VSP, we can still reveal this very, very subtle 4D. So that's a very encouraging result from DAS-VSP. So my last example about DAS-VSP is also 4D, but this time it's a different migration algorithm, and also this time it's 3 wells combined. And here on the left, you can see the regular cutoff migration that is noisy, and you have some. When you look at the 4D, you have a lot of residual as well. And when we apply the least squares migration, the image itself is much better, and the 4D, the time lapse is also much better. And if we map the lower reservoir here to the map, and you can see the 4D signals, the distribution of the 4D signals, and they are consistent to some extent, to a large extent, consistent with the same 4D derived from OBN. Okay, then we'll talk about some surface dust examples. I also have a couple of examples for this section, but this time I just want to highlight that the reason that I have a couple of examples for surface cable is because they all use different type of cables. So this is simply to tell you that you can acquire dust from all different types of cables as long as that cable has an optical fiber. So the first example here is the dust acquired. It's a 2D dust acquired from a subsea power cable. It's a cable connecting two infrastructures. So on the left is the 2D dust image, and on the right-hand side is the full 3D tool streamer. You can see the reservoirs are quite consistent. There are two reservoirs here, and here those are the gas reservoir, the upper reservoir, and there's a deeper reservoir as well. Both can be nicely imaged by, even it's just a 2D dust. So the second example is using what do we call it, the DCFO cable, which is this cable. As you can see, this is the cable that connects the production template to the platform. So it has a fiber inside as well. So we tested to use this fiber to acquire dust, and how can we extract from this data. And this is the imaging result. And on the right-hand side, you can see the two dust images. One is PP, the C is PP, and the D is PS. Remember I mentioned earlier that surface dust record very strong PS signals. That's actually, that's a biggest trouble for PP imaging, but if you do PSE imaging, it turns out to be a very good thing. So you can use that very strong PS to generate a PS image. And we can compare these two images against the same image, but from the OBC data. The next example is the dust acquired from, this time it's a power cable again, but what makes this example special is this is a long-range sensing. As you can see, this red one indicated the power cable from shore to offshore infrastructure. And the blue polygon here indicates the seismic survey area. And this is about 100 kilometers away from the shore, and where we plugged the interrogate box, or where you send the laser pass and receive the laser pass. So as you can see, this is very fast. It's more than 100 kilometers, and back and forth for the laser light is 200 kilometers. So this was actually a big question mark before acquiring this data set. What you can still see after the light travels 200 kilometers. And now you can see the imaging result on the left from this dust cable, and this is a 2.5D, so it's a single cable, but with a very dense 3D shots above it. When compared to the 3D tow streamer, you can see not only the shallow part, the overburden is quite nice, but also even down to 4 and 5 kilometers. You can still see the reflectors being nicely imaged from this dust data. So this is a very good, very encouraging example. So the next one is using the PM cable itself. Remember the first example I mentioned that using those colorful cables, the blue or the red or the green ones, those are the DCFO control cable. But as I explained earlier, that in the PM system, there are ocean bottom nodes that are being connected by fiber optical cables as well. So there's an opportunity to acquire dust using those PM cables. As you can see, there are many cables. So if you can acquire dust from all of these cables, you're going to have a very massive dust data. So that's a very good idea to test. And here you can see the result of which is on the right-hand side of the dust acquired from single cable of that PM system. Again, when acquired with the PM itself, you can see the main reflectors being generated, and you can also see the events in between The green and the red horizons, that's where the reservoir is, and in between there's two lines, there's two horizons. We also have a 4D being extracted from this experiment, and which is the result on the right-hand side. And on the left-hand side of the very first panel is the 4D from the full PM. This is verified 4D signals and highlighted in these two yellow circles. To make this more comparable to the DAS, because the DAS is just a single cable, we regenerate this PM4D, but you only use one cable from the PM. You can still somehow, it becomes much more noisier, but you can still see the 4D signal within these yellow circles. What is encouraging is that you can see similar events, similar energy at the same location. And this is our initial result. As you can see, there are a lot of noise, 4D noise, and above the reservoir. And our final result, we actually improved this a lot. But unfortunately, today I don't have that to show you. Okay, moving on to next example. This example is also quite special. And the special part for this example is that this is DAS acquired from lit fiber. So people probably normally think that you have to have a dark fiber or spy fiber to acquire DAS, but that's not the case due to the advancement of the technology. That now there's a technology called L-band DAS. So you can acquire DAS from a lit fiber without interfering the ongoing traffic in the cable. Let's say if you use a telecom cable, that if you do L-band DAS acquisition, it won't have any impact on the ongoing internet traffic. Because that one is on the C-band, just a different wavelengths of the light you inject to the cable. They won't interfere with each other, so it's individually, completely individually. So, and here you can see the quality of the DAS data on the left, and compared to the PM, it's still quite nice, even you acquire from L-band, not the traditional C-band. And the last two examples is about the land DAS. All the examples I have mentioned so far are from offshore. That's where the majority of our work. But we do have some land experience as well. And this is one surface land DAS. On the left is the shot gather. You can see the very nice reflection from this ore body here. And you can image using the DAS data as well, and compare to the maps node. Again, every time when you compare to the conventional seismic, it's not as good as the conventional seismic, but you can see the major reflectors. The last example is a land DAS VSP. This is it's a VSP. So this is also to image mineral. I think in this case it's a copper. And you can see this orange line that indicating the shape of the copper body, and the very first image is from the surface geophone, surface geophone, and then the second one is from DAS VSP. And what is very nice is you can see how the flank of the copper body being imaged. And to verify that, we generate some illumination study or illumination heat count. You can see indeed for the DAS VSP, there are a lot of much more illuminations from the DAS VSP compared to the surface geophones. One more thing we did on this data set is FWI, to run FWI together with the surface seismic. This diagram or this image on the right-hand side shows the red curve is the input velocity profile to FWI. And the yellow one is the FWI using only the surface geophones. And the green ones is the FWI used both the geophones and the DAS VSP. And when you compare this FWI result against the sonic log, you see the result is much closer to each other. So it's much more accurate. Okay, then a little bit more beyond imaging. I will just mention this very quickly. I'm aware that we don't have much time left. So the one thing is FWI. I'm gonna skip this one because very soon you're gonna see a very good FWI result will be published. Will be better than this one. Another thing is about the seismic inversion use that data set. This is about the amplitude because it's a well-known issue that how much amplitude you can trust from dust, especially the very famous the angle sensitivity issue for dust. And here on the top you can see the different angle stacks from dust, and the first one is the near angle from dust. By the way, this is a surface dust, and obviously you can see that the near angle has a much poor quality than other angle stacks, and also lower quality than the toe streamer, which is the bottom row. So even this is because of the directivity, and even the near angle is very poor like this. But when we do the seismic inverting, we can see the result of the acoustic impedance on the left, and the VPBS on the right. When we compare this dust against the toe streamer, they're actually quite comparable to each other. So it's so that is to say that the amplitude of dust is not completely useless. We're lacking of the near angle, but still, to some extent, it still give you a good seismic inversion result. And finally, and it's a passive example, and you can use the passive dust to look at or to monitor the microseismicity or look at an earthquake. This is an example from Northern Light and CCS, and this is the processed dust. The raw dust is so very noisy, but this is the processed one. You start to see the storm S arrival and P arrival. And we use different method to look at the center of the location of the earthquake. You can see the different method give two different output, but they're fairly close to each other. And when compare to the one that located from the land-based stations, because they're quite different. The two locations from the dust close to each other, and quite far away from the land station derived location. And I personally believe the right ones, from those ones, are more convincible. Okay, to summarize this talk, so there are pros and cons for dust. The first thing is the sensitivity of the dust. It's very sensitive. On the good side, you can detect a very subtle signal, very weak signal. But on the bad side, it's so sensitive, it just record all the noise. So that's give you a very high noise level. Then dust has its continuous recording along the fiber, so you have very dense spatial sampling, as we all know that, and it's cost effective and it's low maintenance because it's a glass fiber. You don't have to repair it, and it is also multi-use, especially for dust VFD. You don't acquire dust all the time, but you can use the fiber for borehole monitoring. So for all these pros, that we can see dust as a great potential for long-term permanent monitoring. This is especially in a carbon storage context. And on the bad side, as I said earlier, it has a very high noise level that we need to handle. We need an effective denoise method to remove them. And also dust is a single component. It's only sensitive along the cable itself. That is to say, a lot of advanced algorithms based on multiple components that we cannot use. And that, for example, a good example is up-down decon. That's the multiple and designature method, but we cannot apply that to dust data. And angle dependency, that's a well-known issue, and not big deal for dust VSP, but it's indeed a problem for surface cable. And dynamic range, because it's a phase measurement, as I explained earlier. Geometry, we need to calibrate for the surface cable, the XY coordinates for the surface cable. And the last thing I want to mention here, particularly I want to mention, is the gap between the dust community and the geoscience community, because our dust has been used for quite a long, I would say, but it's new. It's only new for us, like geoscientists, but it has been a technology for many years in other industry. We don't know, as a geoscientist, we don't know that much. We don't know that much about the dust interrogator itself, how it works. We know the principle, but we don't know how it works exactly. For example, those parameters like a gauge length, the size of the laser pulse, the rate of the laser pulse, all of this will affect your recording will affect your signal to noise ratio and the amplitude of the dust, but we don't know how to model that as a geoscientist. When we do the dust modeling, we still do it in a traditional way. We model the velocity and or pressure or velocity, and from that we get a strain rate and then treat that as a dust modeling, but we don't consider the optical parameters. That's not because we don't want to consider, it's simply because we don't know how to consider. So that's a gap between the two communities. Okay, I think that's all. And by the way, all the examples that I presented today all the data is processed by Viridien. So I have a list of published papers here. But if anyone is interested in any of these examples or would like to discuss more, please feel free to contact myself. And thank you, everyone. I think we don't have that much time left for questions. But, let's see. I can't read the questions.
Thank you, KP. I can pick a couple of questions. Thank you for the presentation. I can pick a couple of questions for you. We have a couple of minutes. So the first one was how reliable is the amplitude of dust signal for time-lapse VSP monitoring EOR projects? So how does the eye temperature affect the fiber response?
Okay, that's a good question. I would have to say that we don't have that much experience for geothermal using dust VSP in a geothermal project. However, if you're talking about the temperature effect on the dust recording, I can say that the temperature will only affect the very low frequency of dust. I would say below 2 Hz. And actually, it's intuitive that you can imagine that the propagation of the heat is much smaller. It's much slower than the propagation of the light. So it will only affect very low frequency, like in a sub 1 Hz of the say, or a couple of minutes scale.
Okay, thank you. So the second question is, I think on the slide 10, which is the one where you're showing the denoise example, ask if you could clarify whether the fiber optic cable was deployed behind the production tubing or behind the casing.
This slide 10. This is all the VSP examples in today's talk using the fibers inside the casing, the clamped to the injection strands, not behind the casing. If you have a fiber behind the casing, then obviously your signal to noise ratio will be better, that your fiber will be better coupled. But then another thing is, if you deploy your fiber in that way, then that fiber can only be used for seismic acquisition. You want to be able to use that fiber for your borehole monitoring. But yeah, you can deploy 2 fibers. It's another option.
Another question, is dust more effective in first break picking? And can we use dust in near surface applications?
Yes, I didn't mention that today, but yes, you can. Yeah, you can do the first break picking and derive some near surface images or near surface velocities that from first breaks, direct arrivals, and the refractions. The refractions are actually very good for dust, surface dust, much better than the reflections. So yeah, you can use it, or we can use it.
Okay, thank you. Okay, I think we've reached the end of this session. Thank you again, KP, for the great presentation, and thank you everyone for joining today. I don't know if Maria Paula wants to have some final remark. Otherwise, yeah, thank you everyone, and have a good day, and see you hopefully at the next webinar.
But there are, sorry, just one more thing that I do apologize. I can now see from the chat, there are a couple of more questions we want to have a time to answer. So please, do reach me if you are interested, or if you have questions. I'm very happy to discuss more on this topic.
Thank you very much, Kunpeng, for your participation in this series, and thank you to all of our attendees today. Thank you, Francesca, also as a representative of the EAGE Technical Community on CCS, for moderating this session.
Yeah, thank you, everyone.
Good to see you all. Thank you for joining us. Have a good day.
Have a good day.
Bye-bye.
Bye-bye.
Bye.